Hello everyone and welcome to our eSeminar today entitled Design Optimization and Sensitivity Analysis of Photonic Integrated Circuits using Physical and Circuit Level Simulations. This is now the third in our current series of webinars. My name is Martin Tim. I'm the host of this meeting. First of all, I would like to introduce our presenters. We have two today. There will be Eugene Sokolov, who is a senior application engineer at VPIphotonics. He has over 8 years experience in the development of market-leading PDA products, particularly in the modeling of modern and next-generation photonic integrated circuits, photonic and optoelectronic devices. Sokolov received his Master's of Science degree in physics from the Belarusian State University, and he's doing his PhD in modeling polarization effects in VCSELs. As second speaker, or first actually in the chronology of things, is Frank Scharf. He's a SIMULIA technical sales director with a focus on optical applications. Dr. Scharf obtained his PhD in electrical engineering from Universität Bochum in Germany. During his graduate studies, he focused on modeling and simulating the plasma sheath in high-intensity discharge lamps. Frank joined CST Germany in 2008 and would transfer to CST of America in 2009. I hand over to Frank to start the presentation.
Well, thank you, Martin, for the introduction. I just want to confirm, can you see my screen?
I can.
Okay, wonderful. Welcome, everybody, to this eSeminar. And yeah, I'm looking forward today. I think we have some interesting topics to talk about. The outline today is that we're going to talk a little bit about the electronics photonics design automation design process. So that's what the EPDA stands for. And as you will see, so some of you might be familiar with EDA, electronics design automation, and then some of you might also be familiar with the P, the photonics design automation. As you will see, it is important to make the right choice in terms of the tool that you want to use for designing your circuit and your IC. So we're going to talk a little bit about that, and then we're actually going to have a test example for a multi-ring filter. Ring resonators are a common element for photonic elements. And what we're specifically going to look at is, okay, once you've designed your filter or your component, your circuit in general, how do fabrication tolerances come into play? So obviously, you can never exactly build something 100% the way you designed it. So how do those variations influence your design choices, and how what kind of yield can you expect? Yeah, so about halfway down this eSeminar, we're going to switch presenters, and we're going to then focus on the VPIphotonics suite of tools. But the first half is a general view, and also introducing the CST Studio Suite as one tool. So the basic PIC design flow is that you start out with an idea, and then you eventually want to create a tape out that goes to the fab. And in between, you know, your idea, you formulate like an overall system design where you have different blocks, and then you need to fill those blocks with life. And for that, you need to actually start your circuit design. In the circuit design, you might have to switch back to photonic or electromagnetic simulation, you know, to confirm the behavior or even extract the behavior of some of the components of your circuit. And very often you also have to rely on multiphysics. For example, thermal tuning is something that is very commonly applied. So that's something you would have to do during the circuit design. But then there's also the layout phase. So after you've designed your circuit, you're going to lay it out, and this is where it becomes interesting for photonic circuits. So for electronic circuits, you usually don't have to go back to the photonics or the Emacs simulation in the layout stage. But for photonics applications, actually connecting two components is a little bit more than just placing a copper wire between the two. So what you have is basically you have an optical waveguide that connects two parts of your circuit. And as a zeroth order approximation. It is a connecting device. It gets your signal from the first part of the circuit to the next part, and this means that the detailed properties like the length, the width of the shape of that waveguide are not critical. However, in real life, an optical waveguide is actually a functional device. It has a certain attenuation. It will influence the phase. And so this could be unwanted, in which case you just have to deal with it, but it's also something that you can actually use, and you can just make the waveguide part of your circuit. And this means that the detailed properties of your waveguide are crucial. And this means that this two-step process here, where you do the circuit design first and then the layout, really becomes one step. That's so-called layout-aware circuit design for photonic design automation. And then our workflow looks a little bit more like this, where you have 4 boxes instead of 5. You would start out with your system design, and I've just added some screenshots here of typical views you might see on your screen during each phase. Then you have the layout-aware circuit design, where you take the circuit behavior into account as well as the influence of the layout. And during that stage, you will very often interact with the photonics or Emacs simulation, and also possibly dive into the multiphysics simulation. So by the way, how often you go back and forth here between the photonics and layout-aware circuit design depends a little bit upon how custom your design is. I mean, you have very often so-called design kits that already contain library elements, and then for those you often don't have to go back to the basic Maxwell's equations. But as soon as you modify those, you customize those, you create your own components, then you always will have to go back to the photonics design. In addition to this modification here, where you have to treat layout and circuit design as one step, there's some additional challenges or differences for the photonics design compared with the electronic design automation tools, which means that just using existing EDA tools is not sufficient. Instead, you need specialized tools for photonics design. And some of those challenges are that you need to use curvilinear layout. So if you do an electronic design, you typically have just 90-degree bends. Makes it a lot easier for the layout and stuff like that. But if you try that for a photonics circuit, you will see that light doesn't actually follow that 90-degree bend. It will just keep going straight. So you have a limited bend radius, maybe like 2, 3, 4, 5 microns, depending upon how much loss you can accept and what kind of technology or materials you use. But basically, this is something that your design tool needs to take into account. On the other hand, you also don't have to worry about shorts so much. Obviously, if you do electronics design and you have 2 wires touching, they're automatically shorted, and you can't do that. So that's why when you do PCB design, you typically have a via going to a different layer, and then it's routed underneath, and then it comes back to this layer through another via. In photonics, you can actually have such intersections, and you can see here that the signal comes from this port, and it goes straight through, and has very low crosstalk. If you have a well-designed intersection, it has very low crosstalk into the other direction here. Then coming to the circuit side, maybe because of historic reasons, and maybe how long people have been doing electronic design versus photonic design and the amount of experience, there's actually no widely accepted SPICE equivalent for photonic circuit modeling that would also include multiphysics, for example. Again, thermal tuning is very commonly applied in such photonics elements, and that would have to be included in that sort of SPICE-like standard. So probably one day we will have something, and then you can have more standardized tools. But at this point, you really have to look at all the tools that are out there, and every tool has a little bit of their secret sauce and special capabilities. And finally, the PDA tools need to support the photonic process design kits, which are slightly different from just the purely electronic process design kits. just to briefly explain what is a PDK, if you're already familiar with it from the electronic side, then probably you don't need much explanation. But basically, it's a list of rules that you need to abide by to make sure that you get a functioning circuit. So basically, you have your existing design, but now you go to Fab A, B, and C, and depending upon the process that they use to fabricate your circuit, you will actually see that the actual outcome is slightly different, and it depends on the fabrication process. And so the exact process is obviously proprietary, but it is encoded in those process design kits. So when you talk to a fab about creating your circuit, they would provide you with this PDK, which often also contains a library of standard elements that they design for you. And then when you put together your circuit, you can use those standard elements, or when you build your own element, you can use the information from the PDK to make sure that the component, that the circuit that you designed will work even after fabrication by that particular fab. So where's CST and where's the CST Studio Suite in this context? So you can see here in the center, I just put a screenshot there of CST Studio Suite, and on the right you can see that we're clearly located in these Photonic and EMAC and the multiphysics simulation boxes. And the way this works now and how it connects to the whole workflow is basically you would create a model, and the model is exactly what you see in the screen here. This example shows a ring resonator with a heating coil on top. So you create your model first, your geometry, and this could be done by hand. You either build it directly or you can import it from some EDA or CAD tools, DXF, GDS2, and so on. Or you can use one of the links. So we currently have two links. One is with Lucida Photonics, and the other one, that is the one we're going to talk about today, is with VPIphotonics. So they can actually directly influence or build models in CST. Then in the CST Studio Suite, you can apply different solvers. And in this example here, you see on the very left a stationary current solver that is flowing through the heating coil. In the center, you see a temperature change. And on the right, you see the corresponding photonic result that takes the temperature change into account. And then once you have all of that information, you can run studies and optimization in the tool itself. You can extract certain values using the result post-processing, or you can take the data and also the geometry and take it back to VPIphotonics, to the VPI Design Suite, or to Lucida Photonics IPGIS, where you then continue to work with the results. Like I said, in this particular presentation, we're going to talk about the automated link between VPI Design Suite and the CST Studio Suite. And it's really quite simple. So basically, it's a bidirectional connection where VPI Design Suite can control parameters of a model, and it can start the solvers directly in CST. And the CST Studio Suite then returns the S matrix, the scattering matrix, which basically contains information about reflections, transmittance, absorbance, and so on, and sends that back to the VPI Design Suite. All the different format conversion and stuff like that is taken into account automatically. So the user does not have to manually copy files around. You can either run this on the fly. So for a particular parameter combination, you just say, oh, I need the results for this, and then you just trigger it and it comes back. Or, and this is especially interesting if you're looking at large number of calculations, you can pre-calculate a number of combinations in advance overnight or so, because photonics or 3D and multiphysics simulations take longer than a typical simulation would take in the design suite, just because of the higher complexity of a full wave 3D simulation. So in that case, you can just pre-calculate a number of combinations, and access them later on, and you can even interpolate between results. So this is nice, and so this is actually a potential workflow where you maybe pre-calculate a set, and then you do automatic interpolation until you've reached a certain point where you feel that, okay, I do need another data point, and then you can just recalculate that on the fly. So in this example here, we're going to look at a ring resonator, or we're going to demonstrate this link by using a ring resonator. This was presented in Optics Express in 2007. And the first thing that I wanted to show you is that it is absolutely possible to calculate this in full 3D. You can see, we nicely see the fields. We can get all the corresponding results here. But it will take a substantial amount of time, several hours, despite even if you use GPU acceleration. So this becomes even more pronounced if you now combine this one arm with another arm to form a diplexer. So again, you have more ports, you have more mesh cells, and so on. The simulation time would just increase. Again, you can do this. You can do it for one example, but if you have to do this multiple times, it becomes quickly infeasible. So the approach is what we call divide and conquer. This will allow you to basically cut your model here into small components or subcomponents, run those subcomponents in 3D, and then connect them on a circuit level. For this example here, you can do this directly in CST, in the CST Studio Suite, where you can run the couplers first. As you can see here, we have one coupler where you just have a bridge in between, the two waveguides are touching, and then you have one where you actually have an air gap in between, and you can calculate that, and then you can calculate the result by using the built-in circuit solver actually. So you can see the two couplers here, and these images here on the right represent clones or copies of the couplers, so it's a symmetric filter in this example. And then you see you get very similar results, but considerably faster. And so this is one example where you could carry it out directly within CST Studio Suite and the connected circuit solver. But if you go to more complex, again, this is a relatively simple example for a circuit. If you go to more complex circuits, you need more components, more standard components, then it makes sense to move on to a dedicated circuit tool such as VPIphotonics. This is also needed if you need to run a large number of parameter combinations due to fabrication tolerances. So if you look at a given fabrication process, and I already alluded to this in the introduction, you can see that you cannot fabricate this with arbitrary accuracy. Instead, you will have variations just due to the way it was created, and typically because you designed your optimal circuit, as soon as you deviate from the optimal combination, you will obviously see some reduced performance. And now what you need to do is you need to study how this reduction in performance will affect your overall production, because you typically don't produce just one circuit, but you produce 1,000, 10,000, 100,000, 1 million. And so there's basically two steps now. So the first is to identify different scales and whether the variations are systematic or random. And so I just want to briefly address 3 scales here. So the first would be the large scale variation. So if you think about a wafer, that's the little blue disk on the right here, and you think about it, it is a layered structure. Typically you have some sort of a substrate, then you have some active layers and so on, and maybe some cladding to protect everything on top. That layer thickness is not constant across the wafer surface. Instead it varies, and typically, because depending upon how the wafer was produced, if the layer was applied by or was created by a spinning process or so, you will see some gradual variations on the wafer scale. So you can see here along the radial position, the layer thickness will vary as shown like this. If you now take the circuits and you put a bunch of them on your wafer everywhere, and then you just look at a single circuit in that whole mass of all the circuits, then you can see that for this single circuit, there's almost no variation in the layer thickness. But if you go to a circuit at a different position on the wafer, then you will see a variation. So this means that you can address the effects of the large scale variations by defining different groups in different areas on the wafer. And you might design one circuit in the center one way, and then the circuits on the outside, you know they're going to behave differently. You're going to adjust for that in the design process already. Similarly, if you now go to the other end of the scale, you go to the very small scale, then there's also variation. So if we look at this waveguide here, which is 500 nanometers in width, you can see that maybe there's an even smaller fabrication tolerance here that, obviously a much smaller scale, and also the magnitude is much smaller. Typically examples for this are maybe surface roughness of the waveguide walls, which is shown here. And this variation obviously is present in every circuit, and affects every circuit in pretty much a similar way. Obviously, assuming that there isn't another large-scale variation that directly affects like the mean value of the small-scale variation. So, but if it's really a homogeneous small-scale variation across the wafer, then again you can account for that in the design process, and you can adjust. You can take that into account during the optimization. The third scale is the medium scale. And then if you look at variations around the length scale of the subcomponents, and I chose an example here, so I'm showing you half of the coupler, and I'm just showing you the variation in the gap width here. And so some other typical examples are the waveguide thickness, waveguide alignments, the way they are maybe aligned with a certain amount of angles or so, and accordingly also gap widths between adjacent structures. And now those variations, if you think about a typical circuit, and every one of them is random. If you now think about one circuit, you have multiple positions where those variations occur, and so you really have a combined effect of each single random variation into one big random variation of your circuit. So it becomes not very predictable. The first two variations are rather predictable, but this one becomes unpredictable. And what you need to do is you need to do some statistical analysis to make sure that your design is robust enough with regards to such variations to function and to yield or to allow you to create a sufficiently high number of functional elements. So this slide illustrates what I just explained. So for our example, we have two gaps. We have two gaps on and two bridges. So we have 4 points basically where variations can occur. If we just want to study two corner points, the minimum and the maximum deviation from the target value, then we have 4 positions to the second power. That's already 16 different combinations. So that would, again, imagine running this in a full 3D simulation, where every simulation would take several hours. It would take a very long time, and reasonably in the number of parameter combinations that you want to study is really closer to 1,000 or even higher. So that would really make it infeasible to treat this in full 3D. And thus the idea is, okay, you're going to extract the behavior of each of the subcomponents, each of the parts of your circuit. You're going to identify how the variation in the fabrication tolerance influence the behavior of that particular part. And then you're going to put it into a circuit level where you then can study statistically many different combinations of those small random variations and do a Monte Carlo analysis for thousands of combinations. And this is exactly what we're going to see in the second half of this webinar, where basically we take our couplers, we study we characterized the behavior of each of the couplers with regards to variations due to the fabrication, and then we put it into VPI design suite, which now has full access to the results and also, basically the full characteristics of each one of the coupler, and it's then possible to do a full-blown Monte Carlo tolerance and yield analysis. And at this point, I want to hand it over to my colleague Eugene here.
So hello everybody. Thanks Martin, and thank you Frank for introduction and for this good overview you did. So my name is Eugene. I'm with VPIphotonics, and we exist more than 20 years, and during this period we created dedicated software tools. Okay, here it is. So we created dedicated software tools for automation of your design, its analysis and optimization as components, circuit systems, as well as networks. One of the tools is called VPI Design Suite. So it comprises itself VPI transmission maker optical systems and VPI component maker photonic circuits. And as soon as simulation and design of photonic integrated circuits is an application we are particularly interested in during this webinar, we will mainly concentrate on VPI component maker photonic circuits tool. So for some specific tasks, we interface with other third-party tools such as CST Studio Suite, for example, and we also provide tools for flexible data visualization and analysis. So our approach of modeling photonic integrated circuits is based on the system level abstraction. So it consists in the segmentation of the whole circuit into separate standard elements, and this approach overcomes the limitations of the standard full wave 3D simulation methods, which Frank mentioned earlier, such as really high computational costs in both CPU time and memory. And it is also important that individual building blocks can be modeled by different methods actually, and providing easy balance between accuracy and speed requirements. So, and yeah, this allows for simulation of real large-scale photonic integrated circuits. So when we talk about dedicated software, what do we mean? Talking about circuit level simulator, first of all, it is sure some library of building blocks, so you can combine them to create your passive circuits or multi-sectional semiconductor lasers, for example. And in addition to this circuit components, there are also components for analysis, and also a huge number of application examples. Further, different simulation domains should be used depending on what you want to simulate. So, for example, passive photonic and linear electronic devices could be modeled accurately and fast using frequency domain, while it doesn't work for active and dynamically tunable devices, where we need to switch to time domain. And it is important that hybrid time and frequency domain could be used when we want to mix different technologies within one circuit, and I mean in active and passive altogether. And it is really important to use hybrid domain for large scale circuits. So further ones would like to use the measured data in the simulation, or extend our library of behavioral and analytical model with some customly programmed modules. So as I already mentioned, we interface with third-party tools, for example, for EDA electronic simulations, for device-level simulations, for conversion of your circuit to layout with subsequent fabrication, and we also do provide process design kits for foundries. And so also dedicated simulation environment includes surely graphical user interface with some useful automated ways of controlling your schematic, and also means of controlling the simulation and design optimization and analysis. So let's come back to our example of 3-ring filter, which Frank started describing before. So in order to simulate this layout, we built up a circuit in a circuit simulator. And in this example, we are using built-in building blocks for the waveguides, which could be modeled by the rather accurately with analytical models, for example, based on coupled mode theory. And these waveguides have certain parameters which could be derived from mode solvers, particularly our mode solver called VPI Mode Designer. But for more complicated components, such as couplers, in our case here, we need to use sophisticated device-level tools such as CST Studio Suite. And so we run simulation for preliminary created projects and extract S matrices, and and have them as input for modeling couplers in circuit simulator. Afterwards, once we have all models in place, we can test the device and obtain spectrum and get characteristics of the design from circuit simulator. So this separation of circuit level simulation of PIC itself and from device level modeling of its building blocks allows for accurate modeling of large scale PICs on a single personal computer and provides sufficient accuracy. And it is worth mentioning that this process is fully automated, so there is no need no manual transferring and converting files between different simulation tools. So it is done all automatically. So CST Studio Suite is called automatically, and touchstone files are automatically converted to VPI's matrix file format. And so there is also no need to calculate these S matrices with CST Studio Suite every time. Instead, they could be cached and reused in subsequent simulations. Moreover, for the components which are different by comparatively small variation in parameters, interpolation techniques are applied. And this means another approach is also feasible. So you can generate database first and with CST Studio Suite and then reuse it in simulations. And together with small simulation times and interpolation and caching features permit to perform optimization and tolerances analysis, which usually involve hundreds and thousands of simulation runs. So fast simulation really matter. So now let me go a bit deeper into this example of 3-ring filter. So such coupled micro-ring resonators are known to provide compact passband add-drop filters with large free spectral range. And our first simple design task could be to design high-order optical filter satisfying some definite specification requirements, such as requirements on fluctuations of transfer function, so-called ripples, on its bandwidth, and on free spectral range, for example. Surely there are more parameters such as insertion loss, steepness of these passbands, and so on, but we concentrate mainly on bandwidth and ripple in our case. So, but if we just plug in all modules together and with some parameters, which we probably can take from the literature or somewhere else, we will most likely obtain something like that. So just a mass, nothing like on the left side of the slide. And so the question is, how can we adjust our parameters in order to obtain from this mass our good add-drop filter? So yes, we need easy automated way to do that. So now having this design task, how should we start? So okay, we have some parameters which we need to adjust. So they are depicted here. We will mainly concentrate on silicon bridge widths, on widths between of air gap between inner couplers, and and difference between ring lengths of inner ring and outer rings. And according to our experience, it is really important to perform preliminarily qualitative research of the device we are considering. So just, to get the idea of how it behaves, which are the main dependencies and which are component characteristics are crucial, and what limitations do we have. So we created circuit with our built-in models, and which use some analytical models, sometimes very simple. So coupler could be characterized just by one number of coupling coefficient. And we perform these simulations, which are really fast. It takes just a few seconds because models are pretty simple, but still this gives us a good idea of how to move further. So for example, on this picture, we can see how difference between ring lengths impacts as a ripple and bandwidth, and we can see that really impact is really high. So based on these results of qualitative analysis for built-in analytical models, we can put together such a table where we can see which parameters influence at which characteristics of our filter. And as I mentioned before, if we concentrate just for simplicity for this particular case on bandwidth and ripple, we will come up with air gap widths and difference between lengths of the inner and outer rings as most crucial parameters in our case. And this allows to greatly simplify our further analysis because we can decrease number of variable parameters and speed up the process of definition what are the circuit settings provided us with the best performance. So to do that, we created this schematic here. So all these couplers, they call CST Studio Suite, or just reuse cached files calculated before by CST Studio Suite. And so we could put this schematic together in VPI design suite, and let me see. And so these guys are different. So these two outer couplers have silicon bridge between them, and we do not vary them. We vary this air gap width of these two guys and the length of this waveguide. And so we need to have a characteristics if our filter is good for the current settings of the parameters or not. So in order to do that, we need to have a figure of merit or objective function, which we need to minimize. And so we use characterization tools here. So we call it spectrum analyzer to analyze the spectrum transfer function of this of the circuit. So it calculates the bandwidth, the ripple, power at maxima, and so on. And then we can use this simple module, simple co-simulation written in Python to calculate the objective function. So in our case, objective function could be defined like that. So just the sum of ripple, of mean ripple, plus inverse value of bandwidth. And if we measure ripple in decibels and bandwidth in terahertz, they will give a comparable contribution to the objective function. We use our simulation script technique to perform this optimization, and particularly we employ a differential evolution method imported from SciPy library, which is Python library. So and we can write this really simple, just few lines code to employ this method and to optimize our circuit, which means to find the settings of this air gap width and the length of this waveguide. So so here's the results. And optimization algorithm converges rather fast. So on my PC it took about 10 minutes and 742 runs to do that. And so the results are shown in the VPIphotonics analyzer. And so we can also see how objective function and parameters values converge to optimum values. And so it is, by the way, it is really convenient that you can roll back to any iteration and see if better results, which fits you better, could be also picked up. And as one can see, optimum transfer function we found is not absolutely flat, so we cannot fully eliminate ripples, which was possible for ideal models a few slides before. And these features are dictated by intrinsic properties of transfer function of our directional couplers, and we cannot, in reality, get rid of them, at least for this design we chose. We have found an optimum design, but what will happen to it if some parameters will fluctuate a little bit, leading to performance fluctuations? So this leads us to an idea of design for manufacturability. So in its narrow sense, this term means that a provided design should be not only optimal, but also less sensitive for process variations and give us high yield. So there are different techniques. We will mainly concentrate and consider corner analysis, sensitivity analysis, and yield analysis. And it is worth noting here that this kind of analysis is usually much more complicated than just running the simulation, and therefore demands specific features. So let me give you an example. So for example, here we have a parameter expression, which is a convenient way of specification some randomly varied parameter. So it just calls NumPy random function, but surely any distribution could be also called here. So it is convenient and easy way to do. However, if we need to change, even for our small example, we already have like about 10 components, and for sure for 10 components you do not want to do this manually. So that's why we need macros. So it's just routine with the scripts which could help us to optimize this routine, to perform it automatically. So further, for control under our simulation, we will use this interactive simulation techniques and simulation scripts so you already saw an example of simulation script when we did optimization. So, and as I already mentioned, a set of instrumentation is also important to have in place. And if you miss something, it is important to have a possibility to add some custom modules to extend this library. Okay, so so here is the example of of corner analysis. So, for example, variation in waveguide widths, they surely result in variation in air gap widths and silicon bridge widths. And so if we have some parameters subject to process variation, as I mentioned already, so process corners represent the extremes of these parameters variations. So for example, assuming Gaussian distribution of our width parameters, the corners correspond to mean value plus minus 3 values of standard deviation. And this leads us to the idea of corner analysis. And so, by the way, when we considered optimization, we regarded our couplers being symmetrical, so meaning this and these guys are the same and this and this. But for process variation, it is surely not the case, and they should be regarded independently. So, concerning m different process variation parameters, we have maximum 2 to the power of m simulations to be run, which for a circuit simulator is not so much actually, so not so many. So for example, in this case we have like 9 or 16 simulations. And yes, we use simple sweeps, so we just sweep the parameters and all combinations could be covered. And a circuit running at these process corners could fulfill specification requirements or not, and thus giving us an idea of how sensitive our design is. And so afterwards we can make a conclusion, so should we change something or should we be happy with that. So though it is really fast and rather good way to characterize your circuit, to justify it. For example, if you have correlated parameters, so this means that some corners will never just happen in reality, so they are very unlikely to observe them. So, but still we perform our corner analysis for them. So this is why other techniques are also used. And another example is sensitivity analysis. So it is based on variation of one variable at a time. So we change one variable and around its optimal value, and all other remains the same, and we can calculate and estimate sensitivity as a partial derivative of our figure of merit. So it could be ripple bandwidth or something else in your particular case, and then we repeat this procedure for different starting points. So this is already rather custom kind of analysis, and it depends on your particular case significantly. That's why we use simulation script. And here it is only part of it shown, so it is more sophisticated than just doing optimization. And we can see here some results of this sensitivity analysis. So we have air gap widths and silicon bridge widths and ring length correlation varied, assuming a Gaussian distribution, and also assuming that the derivative of our sensitivity will also have the Gaussian distribution. We can measure mean value of sensitivity and standard deviation, and this gives us these graphs. And it is really convenient visualization way of how our how our circuit is sensitive to some parameters. And for example, we can see here that mean value for sensitivity to air gap width variation is really high, meaning that our initial assumption that air gap width is really essential parameter for our design has this quantitative proof. And finally, the last example of analysis is a yield estimation. So we can see here an interface tool which we can use. So it allows for variation of the parameters, air gap again, and silicon bridge widths. And again, we assume Gaussian statistics here. And we can define which figure of merit we analyze and what are the limits we put on this figure of merit. For example, in the case of ripple, it could be like our ripple should be less than 3 decibels, and we can specify it here. And the simulation is automatically run 700 times, and so number of failed and passed trials calculated automatically, giving us yield. So here is the results of this yield analysis. So we can see the distribution, a histogram of how ripple for the 700 runs is distributed. And so for 3 decibels limit, yield is 98%, which looks to be good, but in reality, possibly not high enough, because we didn't take into account other process variations and other sources of variations. So probably we really need to change something to make our circuit more robust to this kind of variations. So yeah, let me summarize. So PDA design flow, certainly it poses certain challenges, and definitely ones need a specialized tool to do that. And so during your design, you definitely need to take fabrication tolerances into account. So not just optimize it, but optimize your design with respect to tolerances which you will have during fabrication. Surely physical level simulation is important. and though it is not always feasible for the full circuit, for individual components, it is important to perform it in order to have realistic results. And combination of VPI Design Suite and CST Studio Suite offers a convenient way of combining full physical level and circuit level simulations, which actually meets above mentioned requirements to the simulation. And finally, I showed you examples how optimization, sensitivity analysis, and yield optimization could be performed using these tools. And yeah, and finally, just the seed for further design options which one can have, and they're really rich options. So so probably you'll need to go back to component level and to change your design, to change your geometry of your components. Probably you need to think about changing architecture of your circuit. So simple example, what it could mean. So we had this inner couplers with air gap width in between, but probably you should switch to MMIs, yeah, to the couplers with silicon bridge between coupled waveguides. So this kind of analysis could be also done. And finally, you should remember that you designed it for some application. And so, for example, it is really useful to combine, if it is for active components, if you should launch some light from some active component, laser or SOA, you would probably need to simulate that, because if you have some reflections on the interface, most likely it will change the spectrum of your active component significantly, or even go higher and to perform system level simulations. So, for example, you designed your PAM4 transmitter, and surely you need to put it in your system to see how it works. Does it satisfy the requirements of this system to perform some characterization, such as, for example, if you mentioned PAM4, such as TD-SEQ, which is shown on these slides. So yeah, thanks a lot for everybody, and yeah, thank you for your attention.